Today we're going to be talking about the meta-learning problem and black box meta-learning. I don't know, this is like the first time we'll actually see some of the kind of core meta-learning topics, which I think is pretty exciting. They're actually pretty cool when you look into how they work. First, some less interesting logistics. So the optional homework 0 is due tonight at midnight. We're also going to be posting homework 1 today, and it will be due on Wednesday next week. We're also going to post the Azure guide today as well. Basically, homework 1 will be using GPUs, and you'll be able to use Azure if you don't have access to a GPU. And we have a guide for getting that all set up and so forth. We'd encourage you to kind of try to start getting set up on Azure earlier rather than later in case you run into any catches or anything like that. Great, so the plan for today, first we're going to be talking about transfer learning, which we didn't get to last time. We'll talk about the problem formulation and fine-tuning, which is the kind of predominant approach for transfer learning. And then we'll talk about meta-learning, including the problem formulation, a fairly general recipe of meta-learning algorithms, as well as a certain class of meta-learning approaches called black box approaches. And if we have some time, we'll also go through GPT-3, although I suspect we probably won't have time for that, and we'll probably go over it in a future lecture. And also, these kind of first 3 bullet points are the topic of homework 1. You'll be implementing black box meta-learning algorithms. So this lecture will be helpful for that. Cool. So the goals by the end of the lecture are to understand the differences between multitask learning, transfer learning, and meta-learning problems, understand some of the basics of transfer learning, and then also get into the details of meta-learning, including the overall training setup and how to implement techniques like black box meta-learning techniques. Okay, so let's get started with transfer learning. So last week we talked about multitask learning, where our goal was to solve multiple tasks all at the same time. And we looked at this objective function where we had a loss function for each task with the corresponding data set for each task. And we were trying to optimize a network that can solve all of the tasks simultaneously and leverage the data from different tasks in order to try to improve performance compared to training a task independently. Now in transfer learning, the goal is a little bit different. The overall goal, you can think of it as trying to solve a particular target task after having solved some source task. And the way that you try to do this is essentially trying to transfer knowledge or information from the source task to the target task. And usually in this sort of setup, you assume that the source task is fairly rich. For example, training on ImageNet is a very common source task, whereas the target task might be something that is more narrow or more specialized, and you want to be able to kind of leverage the rich and diverse information from the source task when trying to solve the target task. Now, one key assumption in transfer learning approaches is that you typically can't directly access the source data during the transfer process itself. And this is unlike the multitask learning setup, whereas in multitask learning, you typically have all the tasks at once, whereas in transfer learning, you previously learned task A, you have maybe some pre-trained weights or something like that about what you learned about task A, but you can't directly access the original data set. For example, if you're trying to transfer from ImageNet to like a medical imaging problem, for example, storing all of ImageNet and using that might be quite expensive when you're trying to solve the target task. It's worth mentioning that transfer learning is a valid solution to multitask learning. You can, if you care about one of your tasks in particular, you can try to solve a previous task and then transfer to that target task, but not vice versa. So in transfer learning, you really care about the target task, whereas in multitask learning, ultimately, you are trying to optimize the loss for multiple tasks. Okay, so a question for you. What are some problems or applications where you think that transfer learning might make a lot of sense relative to multitask learning? Any thoughts? Yeah?
Image classification, maybe classify images very specific. Like you could just use like consistent models and just transfer those.
Yeah, so the example was image classification, where maybe you have some existing model for image classification, and then you want to transfer that to a different image classification problem. Yeah?
Limited data in task B.
Yeah, so if you have limited data in task B, you want to leverage kind of the information from task A. And that's a scenario where probably transfer learning would make a lot of sense. Multitask learning may also make a lot of sense if you have the information in task A available. Yeah?
We have a lot of unsupervised data that you can then use to fine-tune the unsupervised data.
Yeah, so maybe you have a lot of unsupervised data, and that's your source task, and you want to leverage the information from that unlabeled data when solving a target task. Any other thoughts? Yeah?
If the source data set is really large, that you're transferring from.
Yeah, so if the source data set is really large and you don't want to have to actually train on this really huge data set when solving your target task, it might be a lot cheaper computationally and more practical computationally to instead try to transfer kind of a more compact representation of the knowledge in task A. Okay, so this is actually one of the examples that I put up on the slides is if your source data set is very large, you don't want to have to retain and retrain on this source data set every single time you want to solve a downstream target task. And then another scenario where it might make sense is maybe you don't actually care about solving both A and B. For example, maybe A is self-supervised, or maybe it's some previous image classification task that you no longer care about, and you really want to focus on this target task B. Then this sort of transfer learning scenario can make sense because it allows you to kind of try to leverage the knowledge from task A without necessarily having to solve task A. Yeah?
The task for the data set for task B is very large, and you could jump start on that meaning on the paper as well.
Yeah, so the point is that the point that was brought up is that you may also have a fairly large data set for task B, and maybe it takes a lot of time to learn that, and you want to jumpstart that optimization process by leveraging a model that you already trained on a previous task. Okay, and so I'll cover one approach for transfer learning, which is referred to as fine-tuning. Many of you have, I would guess, have encountered fine-tuning in other courses or other experiences. And the way that fine-tuning works is you have some pre-trained parameters that were trained just on your source task. And then you run gradient descent on the training data for the new task. So you initialize the weights with something that was trained on task A, and then you run gradient descent. This is just showing one step of gradient descent. In reality, you would run probably many steps of gradient descent on the data for your target task. Okay, and so if you actually look at transfer learning compared to training from scratch, you can see pretty large performance gains in a number of scenarios. So for example, if you pre-train on ImageNet versus if you start from scratch with a random initialization, you can see an improvement from 41 to 58% on the Pascal dataset and 35 to 52% on the Sun dataset. And so in this case, the pre-trained parameters came from ImageNet. But in general, the pre-trained parameters may come from a variety of sources. They can come from ImageNet. They could come from models trained on a large language corpora using some sort of unsupervised or self-supervised technique. Really, whatever large and diverse data set you might have access to, or whatever large pre-trained models you might have access to, that you think might be related and useful for the target task you're trying to solve. And one of the things that's really nice about this sort of technique is you don't even have to actually store the source data set anywhere. In many cases, you can actually just go and download a pre-trained model from the internet and run fine-tuning from there. So these kinds of pre-trained models are often available online, and they're reusable for many different target tasks. Okay, now, all this said, fine-tuning is like a really great technique, but there are some kind of different practices to try to get fine-tuning to work better. And this is really more of an art than a science. So people have considered a number of different practices, like trying to fine-tune with a smaller learning rate than your original learning rate. And the goal of this is to try not to erase the knowledge in the pre-trained model. Sometimes it makes sense to use a smaller learning rate for earlier layers because often the earlier layers of the network have information that is more general about the inputs. Also, some models just completely freeze the earlier layers and only fine-tune the later layers or gradually unfreeze them as it has learned the higher level representations. Another approach is to simply reinitialize the last layer or put a head on top of the network that you're going to train, but keep everything else fixed. And then in general, there's all these kind of hyperparameters or things that you can try with fine-tuning. And oftentimes what you can do is you can just hold out a subset of your target task and use cross-validation to figure out which kind of technique works best for the fine-tuning process. Okay, and it's also worth mentioning that architecture choices here also matter a lot. So for example, residual networks have been found to be work quite well for fine-tuning because they lead to gradients that are better behaved. Great, any questions on fine-tuning? Okay, and so here's an example of fine-tuning on a text classification problem where it was pre-training using a language model and fine-tuning using 3 different text classification problems from IMDb, Trek6, and AG. And what you see here is each of these plots is showing the x-axis is showing the number of training examples in the target task, and the y-axis is showing the validation error rate on that target task. And so what we see is overall, of course, as you have more examples, you do better on the target task. But we also see a big improvement between learning from scratch. See a big improvement from using the pre-trained model compared to learning from scratch. The other thing that you might notice here is that as you move towards fewer and fewer training examples, fine-tuning still helps a lot over learning from scratch, but it doesn't work as well as when you have a lot of examples. And so, for example, when you have only 100 training examples or even fewer than 100 training examples, you might not expect fine-tuning to work very well. Yeah.
Right. So this might be permitted, but why is the semi-supervised you're doing better than the supervised?
Yeah, so in this case, what the supervised versus semi-supervised means is that the supervised example is using labeled data from the target task, and the semi-supervised example is using that labeled data as well as unlabeled data that's also available. And so it's using additional data in this case, and it's running supervised learning on the target objective, the classification objective, and it's using the unlabeled data with a language modeling objective. And so that's why it's referred to as semi-supervised. Yeah?
Could you just explain why it doesn't work well with small target task data sets? Because my intuition is it may overfit small target data sets.
Yeah, absolutely. So when the data set is small, essentially what happens is that it either still overfits to that because you are still training on a relatively small data set, or maybe you tune the hyperparameters so that it doesn't overfit, but it doesn't change the source model enough to actually sufficiently solve the task. Okay, yeah.
Is that also the reason why they only started with 100 training examples like from the get-go?
Yeah, exactly. So that's why this x-axis starts at 100. If you move even further to the left, it gets even worse. Yeah.
Are there other ways of encoding like knowledge from the training task or training the data other than just transferring the weights over to the new set?
Yeah, so transferring the weights is certainly the most popular approach. There are other approaches in the domain adaptation literature. You can also use things like multitask learning. Most of the other approaches for transferring information either just transfer the weights typically, or they assume that you have access to the data, all the data from the source task, and try to use that data instead of using the weights or in addition to using the weights. And then, of course, another approach that we'll talk about right after this is how meta-learning can actually be useful for leveraging the source data in a way that can actually work well with very small amounts of data of the target task. Yeah?
One question in the chat. Can you transfer learn across different network?
Right, so the question is, can you transfer learn across different network architectures? In general, with fine-tuning, you do assume that the architecture for the source task and the target task is the same. You might add a couple layers on top, or you might chop some layers off of the source architecture. But in general, it's going to be a fairly similar architecture. At least the first few layers of the network have to be the same. Okay, so now let's talk a bit about meta-learning and how we can actually learn target tasks with very small amounts of data by essentially learning how to learn different source tasks. And so to start, let's actually just cover the problem statement of meta-learning. And this is the problem statement that we'll consider in this class. There are other ways to think about the meta-learning problem statement as well, and happy to chat about those separately. Okay, so there's really two ways to view meta-learning algorithms, and we'll discuss both of them in the course. One we'll refer to as more of a mechanistic view, which is thinking about how to implement algorithms and how they actually work in terms of their underlying mechanisms. And the second view is more of a probabilistic view, which ties into nice intuition with regard to probabilistic graphical models and thinking about things in terms of priors and posteriors. And so from the mechanistic standpoint, the way that meta-learning algorithms work is they essentially have a model that reads in an entire data set and makes predictions for new data points. And then you train this network itself with a metadata set or a data set of data sets such that it's kind of trained to read in data sets and make predictions and generalize from data sets across a set of data sets. So essentially it's learning how to learn from a set of data sets, and this is why it's referred to as meta-learning. So it's explicitly optimizing for the ability to learn from data sets. And then the more probabilistic view is, instead of thinking about it in terms of reading in data sets and making predictions, it instead views the meta-learning process as trying to extract prior knowledge from a set of tasks, and then using that prior knowledge to quickly solve new tasks. And then from this standpoint, you can essentially view it as learning a task that uses a prior and a small training set to infer a posterior over the parameters for that new task. So we're going to be talking about both of these views. For now, we're going to focus primarily on the mechanistic view. But when we talk about Bayesian meta-learning, we're going to talk about the probabilistic view. And the probabilistic view does end up being quite nice in terms of intuition and thinking about the problem. But I think that the mechanistic standpoint is a little bit easier for just understanding how things work from the beginning. So we'll have Bayes come back later. So how does meta-learning work? We're going to run through an example of kind of the problem setup and the training setup. And then we'll talk about how algorithms go about solving this training set. So as we saw in the first lecture, we are going to look at an example where we want to be able to perform image classification. And we're given a really tiny training data set. This training data set has 5 examples, 1 example of 5 different classes. And we want to be able to use this tiny training data set in order to classify new examples. So this is essentially our test set. And of course, like we saw in the first lecture, humans are pretty good at solving problems with very small amounts of data, including in scenarios where you haven't seen these classes before. But if you train from scratch, or even if you fine-tuned on this tiny amount of data, you wouldn't be able to generalize to new examples very well. So this is what we want to be able to do essentially at a test time. We want the model to be able to perform this few-shot classification problem. And so the way that meta-learning algorithms work is they try to create a training setup that prepares the model to solve these kinds of problems. And the way that you can do that in the standpoint of machine learning is that this is what you want to do at test time, that at training time you should give it examples of solving problems like this. So what we can do is we can give it kind of mini train sets and mini test sets and train the model to solve these kinds of problems so that it can generalize to test examples from training sets, so that after it's seen kind of all of these different training tasks, it can eventually solve the problem at the bottom. So each of these rows are just different classification tasks. These are constructed using a set of training classes. And then, so this is kind of the meta training process. And then at what I'll call meta test time, we want to be able to learn a new task using the tiny training data set. And this is a kind of a held out test task. And it has a training data set and a test set. And this training set and test set exactly mimics the kinds of training sets and test sets we'll see during the meta training process. Yeah?
Yes, sets the rectangles in the meta training phase, but are not like technically kind of like the one and see the learn from them.
Yeah, exactly. So the examples on the top right in the blue rectangles, these are not actually held out from the meta training process. They are being used to test the model's generalization on that particular task, but these are kind of the training classes. And then these are the examples that are completely held out, these examples down here. And these will be kind of, classes that are held out from the training classes used for meta training. Yeah.
Is transfer learning superior to meta?
Yeah, so the question is transfer learning superior to meta learning when there's a domain shift? And in particular, one thing that you might notice is that we're trying to make it so that training and test time match. So that we're essentially preparing it for solving this sort of classification problem. And if you do have a task that is out of distribution from what you're training it on, then it may not work well because that's not what you prepared it for. And in those kinds of scenarios, transfer learning can sometimes perform better than meta learning kinds of approaches. Now, each of these rows corresponds to a different image classification task. But in reality, you can really replace image classification with really any sort of machine learning task. You can replace it with different regression problems. You can replace it with different language generation problems, different skill learning problems, and so forth. And you can also potentially combine it with really a variety of machine learning problems. The most important thing is that the task that you're seeing here is within the distribution of tasks that it sees during meta training. So we're essentially raising machine learning up to the level of tasks. Okay, so you can think of the meta learning problem as given data from a number of tasks, quickly learn a new test task. And one key assumption is that these meta training and meta test tasks are sampled IID from the same task distribution. And so we can think of it as having some distribution over tasks and then sampling them from that same distribution. And like before, like in multitask learning and transfer learning, you also want these tasks to share some structure. If they are completely random tasks, then even if they're drawn IID, you won't be able to do better at the test task than learning from scratch. Okay, so what do the tasks actually correspond to? I gave an image classification example on the previous slide. It could also be something like recognizing handwriting digits from different languages. And this is the example that we'll see in homework 1. It can also correspond to giving feedback to students on different exams, where different exam problems correspond to different tasks that you need to be able to give feedback on. We'll see an example of this in 2 lectures, I think. It could also correspond to classifying species in different regions of the world, where different regions correspond to different tasks. It could also correspond to a robot performing different tasks as well, where it wants to learn a new skill or a new task by leveraging experience solving previous tasks. Now, another natural question is how many tasks do you need for this whole meta training process? And in general, it's really a case of the more the better. Essentially, meta training or meta learning algorithms treat tasks as data points. And analogously, in machine learning, the more data you have, the better. And so in meta learning, the more tasks you have, the better. Yeah?
Are you trying to gain some intuition for what a task distribution is? What does it mean for 2 tasks compensing distribution?
Yeah, that's a great question. So there's different ways that you can look at the there's different ways of representing different kinds of tasks. Let me think of a good example. So, I mean, as one simple example, you could say that you want different tasks correspond to like a robot running at different velocities. Like one task is to run like as fast as possible. One task is to like do a very slow trot, something like that. Then your task distribution would correspond to correspond to essentially just different velocities. And you would assume that you have some distribution of velocities. You have some distribution of velocities, and the training tasks are sampled from that distribution of velocities, and the test tasks are sampled from that distribution of velocities. Now that's one example. There are also going to be examples where you might not have this nice parametric way to specify tasks. And in those cases, it gets a little bit murkier, per se. You can also think of, when we define tasks 2 lectures ago, we defined it as kind of a distribution over x and a distribution over y given x, at least for supervised learning problems. And in this case, you can, if you can essentially somehow parameterize these distributions, then you can think of the distribution over tasks as being a distribution over those parameters. So if these are parameterized by phi, for example, then you would assume that you have some distribution over phi. In practice, you may not always have this nice parametric form for your tasks. Yeah?
Just the robot example. Sorry if I missed the point, but like, what's the difference between having like these different tasks and like different velocities versus just having like one big data set? Does that make sense?
So you're asking what's the difference between having like breaking it down into different tasks comparing to have like a single data set with all the tasks in it?
Yeah. I don't know if there's a distinction.
Yeah, so essentially the important thing here is we want to be able to learn a new task. We want, like, maybe the robot has acquired a bunch of previous skills and now it wants to like learn how to ride a bike or like skateboard or something like that. One of the things that's pretty important in the meta-learning problem statement, and we'll see why this is later, is to actually break down the previous experience into these different tasks. And that allows you to try to extract the shared structure between those tasks and ultimately learn a new task. And if you don't have it broken down into those different tasks, then it's much more difficult to try to very quickly learn a new task like skateboarding. Yeah?
From our discussion yesterday, for velocity learning, is tasks have both data sets and loss functions. Is the distribution here? I mean, it seems like to me the distribution you have the same data set and different loss functions, and you're looking at distribution of your loss functions, so you distribute the data set and also the short distribution. Is that true? And also, if so, is there like one that is more common?
Yeah, so I guess I should have also said you have a loss function for each task as well, and that could also be potentially parameterized or something. And yeah, so different tasks can vary in these different ways. They could choose to only vary in this way, they could choose to only vary in this way, and so forth. I think that it's probably most common for different meta-learning tasks to vary in the data and not in the loss function. But in principle, you can vary any aspect of it, or choose to not vary any aspect of it as well. Yeah?
The loss function is the same across tasks. Is there some kind of preliminary analysis one can do to figure out if the problem will be best solved through meta-learning or just lump it on one data set and train something on that? Is there a way to kind of determine beforehand which approach to take?
Yeah, so the question is there a way to determine ahead of time which approach to take, whether to take a meta-learning approach or a transfer learning approach? In general, there isn't any formula that will tell you which approach to use. Although hopefully over kind of the course of the kind of next couple of weeks, you'll be able to get some intuition about which approaches might be more suitable. Yeah?
Within the methodology problem, is there science to in which order we learn tasks in very creative time to make it easier to learn a new task to test on?
Yeah, the question is there a way to, is there something that tells us how to order the tasks in a way that will help make it easier to solve the test task? I guess the short answer is that's an open problem, I think. Also, one interesting problem beyond that is not even ordering, but can we pick the set of training tasks that will be most useful for learning the target task rather than, and then from there also picking the ordering and so forth. As we'll see later, we do actually train on all the tasks at once, essentially, rather than training on them one at a time. And there is a little bit of work on studying curriculum learning, but in general, it's an open problem. Yeah?
The task is continuous, like the velocity of the robot working is a continuous.
Yeah, so the question is, what if the task is somewhat continuous, like the velocity of a robot? In that case, we will still be sampling tasks for training, and so we'll be sampling numbers from a distribution over velocities. You can choose to sample every single iteration of training, and so you don't necessarily need to have a finite number of tasks. If you have infinite, the more the better, and that's great if you have access to that. Yeah? Yeah, so the question is, how do you ensure that tasks are drawn IID from the distribution? It really depends on the problem. You want to, the most important thing is to try to have the test task be drawn from a similar distribution, and not be completely out of distribution or like significantly harder or significantly easier than the task that you saw during training. Okay, one more question.
One more question. So what are the sub-strategies to overcome the domain shift problem in meta learning?
So the question is, what are some strategies for overcoming domain shift? We'll talk about this next lecture a little bit. Okay, and then we can answer more questions a little bit later, or maybe some of the slides will answer them. Okay, so I want to go over some terminology. So in the example that I showed before, we have these meta-training tasks and meta-test tasks. Each data set, each training data set for a task can be referred to as the task training set. And so if a task is indexed with I, then I'll use dtrain I to refer to that. And then each task also has a corresponding test set for that task. Sometimes these are also referred to as the support set and the query set. I'll also be using this terminology. It's helpful to use support set and query set for these train and test sets because it distinguishes it from training tasks and test tasks, or meta-training tasks and meta-testing tasks. And then in general, if we want to learn with a small number of examples, we refer to that as k-shot learning, where we assume that we have k examples per class. Or if you're like in a regression scenario, you just have k examples total. So for example, in one-shot learning, we'll have one example per class. And then in n-way classification, essentially the model will be choosing between n different classes. So a question for you. What is k and n for this example here? Yeah?
K is 1 and is 5.
Yeah, k is 1 and n is 5 because we're doing 5-way classification, and each of our support sets has one example for each of the 5 classes. Okay. So this is kind of the notation and terminology that we'll be using throughout the next several lectures, including in the homework. Yeah?
What the test is that is actually prompting the model to do? Like, is there 2 images and it's kind of classified from that?
Yeah, so essentially what we're going to be trying to do is learn from the training data sets, and we want to be able to learn from the training data sets in a way that generalizes. We don't just want to be able to like memorize the training examples. And so these test sets shown in the red boxes are essentially going to be testing the model's ability to generalize. I'm showing just 2 examples here for conciseness on the slides. And in reality, this could be different sizes. It could be 1 example per class. It could be larger than that. It could be smaller than that. It should be at least 1 to measure generalization, but it could be different sizes. Yeah?
Does the n include the classes during meta testing as well, or just the classes being during meta training?
Right, so n includes essentially the number of the classification problem that each of these tasks involves. In reality, you may be doing meta training with many more than 5 classes or many more than n classes. So for example, you might notice here that like we see classes like bird, mushroom, singer, piano in the first example, and we see classes like landscape, tank, barrel, that sort of thing. And so we actually have more than 5 classes that are being used in this meta training process, but the classification problem that's being solved at meta test time is a 5-way classification.
The n is both tasks.
Per task, exactly, yeah. Yeah.
Is there a work for better problems for more or less classes?
Yeah, so the question is it easier or harder to learn with more or less classes? If n is larger, that's harder because it has to distinguish more classes from one another. So larger n means it's harder. If you have a lot of classes to choose from in the meta training process, but n is held constant, that generally makes it easier because you have more data to learn from and essentially more tasks. Yeah?
To clarify, does it need to be, does it need to be homogeneous across all of training, and if so, why?
Yeah, that's a great question. So does KNN need to be the same across all the tasks? It doesn't. It can be different for different tasks. You want to make sure that you don't have a harder meta test task than at meta training, and so you shouldn't set n to be like larger than any of the training tasks. And for simplicity, it's all the same here, but it can be different for different tasks. Yeah.
Should there be a fixed number for each task? For example, in a third row, I can take the dog and the lamb as the same class because they are all animals. And in that case, the K would be 4, but I can also think dog is 1. Dog and lamb is 2 separate classes. So in that case, the K would be 5. So should K be fixed for each task?
Yeah, so K can be different for different tasks. You don't, so it can be different. In this case, it's considering like dogs and lions to be different classes because it's a more fine-grained classification problem. But in general, K can vary across the tasks. Okay, so to recap the different problems, we talked about multitask learning where we want to learn a set of tasks, transfer learning where we want to transfer from one task to another task. And in the meta-learning problem, we assume that we have a set of previous tasks and we want to quickly learn a new task. And so this is somewhat similar to multitask learning in that we have multiple tasks. However, unlike multitask learning, we're trying to learn a new task, and we're trying to learn a new task efficiently. And it's related to transfer learning in the sense that we want to learn a new task, except that we actually assume that we have multiple previous tasks that we're going to learn from during the training process. Yeah?
Like conceptualization, is it usually the case that we assume that the meta training phase is done with like essentially blindly to the new task?
Yeah, exactly. So we typically assume that you don't have access to these training tasks you don't have access to the test task and the training task at the same time. If you did have access to them at the same time, then you could use multitask learning. And instead, we're going to be in a scenario where we kind of meta-train some sort of prior from the tasks and use that to quickly solve a new task. Yeah?
Can you go back one slide?
Yeah. Sorry, not that slide, this slide.
Yeah, so would it be possible, because like, at the end of the day, it's trying to do like an n-way classification for all of these data sets, right? So do we even need any shots? Can we not just do 0 shots? Because at the end of the day, like the overlaying goal, like the goal is the same, right? I give you 2 images and 5 images and tell me which classes they are. Can not just like throw it out there and just see what happens? Does it need a shot at all?
Yeah, so I think the question is that can we just kind of combine all the classes together and just do kind of standard classification?
Basically 0 shot learning.
0 shot learning. Okay, so great. So so the question is, can you do 0 shot learning? In general, so if you've never seen like these classes before, if you've never seen ice cream and dogs and so forth, you won't necessarily know what the corresponding class label is for that. We are going to see approaches next week that look a little bit more like 0 shot learning in some way. But in general, typically for 0 shot learning approaches, you need some description or some metadata or something to tell you about what the task is. Otherwise, you simply just won't know kind of how, like what to output for lion, for example, or what to output for bull and so forth, like what the model should be outputting, what the class label corresponds to. Yeah?
Except if you phrase it in a Mexican framework, for example, when you say given these, say for each test image, which image is closest for.
Yeah, exactly. So next week we'll cover metric learning approaches that are going to look a little bit more like 0 shot learning. That will be on, I think, Monday next week. And those will look a lot more like 0 shot learning approaches. Yeah?
It seems like the worst advantage of meta learning is just that you can learn the new task quickly. Are there examples where this will actually work, where like somebody's going through the new task and like learns it on like a device or
Yeah, so the question is, are there examples of actually being able to like learn new tasks quickly using meta learning? And I guess the short answer is yes. We've seen it. I'll try to cover some different applications of meta learning in the next few lectures. But one example that we'll see, we applied meta learning to education, and we were able to essentially give feedback on an entirely new exam, where instructors of the course essentially gave feedback on a small number of examples, and then the system was able to give feedback on the remainder of the students' exams. Okay, so going back to the problem setting, in transfer learning and meta learning, it's generally assumed to be impractical to access the previous tasks, because maybe we have a lot of data and we don't want to continuously retrain on all of those previous tasks and data. We want to be able to just quickly, both computationally and data efficiently, solve a new task. And in all of these settings, we want the task to be able to share some structure. Okay, so we've talked about the problem. What is the approach for actually going about solving this problem? So one way to view this problem is kind of in contrast to supervised learning. So in supervised learning, we have inputs x and outputs y. We learn a mapping from x to y using a data set of input-output pairs. And in meta learning, or kind of the supervised learning variant of meta learning, now instead of having kind of input x, output y, it's a little bit more complicated. So we have a training data set. This training data set has k examples. And we want to be able to learn from this training data set in a way that allows us to classify new examples x test. And so if we want to classify new example x test, then the output will be y test. And so in some ways, you can view the meta learning process as trying to learn a mapping from a data set and a test example to the corresponding label for that test example. And the way that we can go about learning this mapping is with a data set of data sets, where each of these data sets is going to have more than k examples. So you can sample k for the training data set and at least one to be used as the test example. And this view is pretty nice, because it means that if we view the process of learning from small amounts of data in this way, then we simply just need to design this function f that can take as input a data set and generalize from that data set. And once we design this, then we just need to optimize it using a set of data sets. So f is essentially representing some form of learning procedure. And we're going to be optimizing this learning procedure in order to learn from data, learn from small amounts of data. And so from this standpoint, we can, when designing a meta learning algorithm, we can essentially choose a form of this learning procedure, parameterize that learning procedure in some way, and then choose how to optimize the parameters of that learning procedure using some form of maximum likelihood objective on the meta training data set. And I'll refer to theta as the meta parameters. These are the parameters that kind of parameterize this learning procedure so that you can learn from data. Okay, so this is the general recipe. Now let's actually talk about one way to instantiate this recipe. And in particular, we're going to cover 3 different possible instantiations. One will be referred to as black box approaches. Another will be referred to as optimization-based approaches, which we'll cover on Wednesday. And the last will be metric learning approaches, or these more non-parametric learning methods. Okay, so the key idea behind these black box approaches is to essentially parameterize the learning procedure as a neural network. And in particular, you can just have a neural network take as input a data set and output parameters of a model from that data set. And then once you output these parameters, then you can just try to predict the label for new data points using a network parameterized by those parameters phi. And so essentially what this might look like is we have some neural network here. It might be a recurrent neural network that takes as input the data points from your training data set, and then uses that to output a set of parameters phi. And then you have another neural network that uses those parameters phi to make predictions for new examples. And so this is essentially detrain and detest, or your support set and your query set. And then you can train these neural networks with standard supervised learning across all of the tasks in your meta-training set. So essentially sum over all of your possible tasks and measure how well the model with parameters phi is able to classify new examples. Okay, and then if we refer to this as kind of the loss function of the parameters phi on your held out data points d test, then we can also write this loss function like this. So essentially we're using f to predict the parameters phi and then measuring how will the parameters phi generalize to test examples. Yeah.
Makes sense to condition like phi I on x ts, like actually have like the test input, like the parameters depend on the test input.
Yeah, so essentially, does it make sense to have the learning procedure take as input the test input and use that in the learning process in some way? I haven't seen that done before, but I could imagine some applications where maybe knowing what you're going to be asked to do at test time is informative for the learning process. Yeah.
I realized that subscribe with parameter phi, so does it mean you would have to individually train a parameter phi for each task, or you can do it like amortize the weight?
Yeah, that's a great question. So I here is indexing the different tasks, and phi I you could actually think of more as an activation of this network rather than actually as a parameter or as weights. It's essentially something that this network is producing. The neural network is outputting weights of another neural network, and then the output of that is being used as weights of this network G here. And so it's not something, phi I isn't something that you actually represent separately. It's something that this neural network is producing. Yeah.
So are you only directly optimizing data here?
Yeah, exactly. So this, as you can see in the optimization, this is optimizing the weights of this network here, and you're not actually optimizing phi. Yeah.
So maximizing the loss, but the log likelihood, like if you're the L gives the log likelihood.
Yeah, so this is showing maximizing the log likelihood. I guess I should also have a negative sign there. This could correspond to the negative loss function, where you're minimizing the negative log likelihood. And yeah, I should essentially put I don't think I have a way to like edit this, but I should put a negative sign in the second two rows on the bottom right. Yeah.
Given that both phi depend on theta and theta depend on phi, doesn't that mean that you're going to train both networks simultaneously? Right? So you need the training data on hand to get done.
So you can think of phi again as a bit of an activation, and so you're not actually training phi in any way. You're only training the parameters of this neural network, and you're training it to output parameters, output weights for another neural network, so that other neural network works well. And so phi isn't actually being optimized here per se. It's only theta that's being optimized. And so now let's look at an example of how we could actually go about training something like this. So what we'll do is we can first sample a task from our set of training tasks, then or a mini batch of tasks. Then we'll sample a support set and a query set, or a train set and a test set from the data set for that task. So say, for example, our task is to classify this kind of dog, landscapes, pianos, and barrels. Then what we'll do is we'll sample a set of images for that particular task, that n-way classification task. Then we will randomly partition that into a training set and a test set. So we'll randomly choose some images to be used as the support set and some images to be used as the query set. Then, once we have a support set and a query set, we'll compute, we'll run f forward to get a set of weights for this particular task. And then we will evaluate how well the network G-phi does on held out examples and backpropagate our loss to update theta so that training it to effectively learn from this training data set in order to classify new examples. And then we can repeat this process, again, sampling a new set of tasks and updating the learner so that it generalizes to new examples. Yeah?
Output loss function, or I guess the output of the network be encoded, because if you're using like a one-hot vector or something, wouldn't the classes that correspond to each position kind of be different every time?
So you're asking how do you parameterize phi I, or? Yeah, that's a good question. So in this particular case of image classification, where you're sampling essentially a set of tasks, you also need to choose the label for each of these image classes. And what's typically done in this sort of image classification example is to, like when you sample in the 5-way classification problem, when you sample 5 images, you just assign a one-hot ID for each of those 5 classes at random. And so you'll assign a label of 0 for barrel, a label of 1 for this kind of dog, a label of 2 for landscape, and so forth. And this does mean that across different tasks, the label of 0 will mean different things. And a barrel might be assigned to label 0 in one task and assigned to a different label in another task. And that sort of approach is actually somewhat beneficial in that it prevents the network from essentially memorizing the classes of the labels of certain classes and allows it to generalize to new image classes which might have different labels assigned. Yeah?
Does it usually remain fully differentiable? Like, can we just take a gradient with respect to data directly from one test?
Yeah, so the question is this kind of fully differentiable, and can we take the gradient of theta directly with respect to the performance on the test data points? The answer here is yes. In general, it should be yes. There are scenarios where maybe you parameterize G in a way that isn't differentiable. But in that case, you wouldn't be able to optimize it as a normal neural network. In general, neural networks are fully differentiable. And so you can essentially just differentiate directly through phi into theta so that you don't actually have to optimize phi. Yeah?
Generally, current lines all weights in G phi already have some of the weights of the transformation.
Yeah, so that's a great question. And we'll talk about that on the next slide. So one thing that you might notice is that if G phi is a huge neural network, then outputting all of the parameters for a huge neural network seems a bit impractical. It doesn't seem very scalable. And so you don't actually need to output all the parameters of a neural network. What you can do is essentially just output something like just the sufficient statistics, or just output the parameters of the last layer of the network, and use other parameters in G that are kind of fixed across all of the tasks. And so one way that you could look at this is we can take the diagram that we had before and replace phi with essentially just the kind of as some sort of hidden vector of like a recurrent neural network. And so we'll have this low-dimensional vector hi, and this can represent essentially contextual task information, and you could have other parts of G that have, you can essentially share some parameters between theta and other parts of G, so it's using both theta and hi in order to solve the task. And so in this case, phi I will correspond to the hidden representation H, as well as some other parameters of theta, which I'll refer to as theta sub G, which could be some separate parameters that are specific to G. In the case of an RNN, it could also be things that are shared with F as well. Now, one thing that could be useful in terms of thinking about this sort of approach is if we recall the multitask learning approach, where you have a network that takes as input a description of the task. You could essentially think of the description of the task as this hi, or in some more general form, you could essentially view the description of the task zi as just corresponding to a data set for that task. And so essentially, instead of conditioning on a task description, you're conditioning the network on a data set. Cool. Any questions on how this works before we move on?
So this is sort of excluding the changing the loss function.
So the question is this excluding, like, does this mean that you have to have the same loss function for all of the tasks?
Yeah, but like just like from my previous question about this.
Right. Yeah, so this is a good question. So actually, I mean, the way that I presented this actually means that, like, in general, I think that people typically assume that you have the same loss function across all of the tasks. In principle, instead of only passing in the data set, you could also pass in information about the loss function. And if the loss function is training across tasks. Yeah.
So just to clarify, so in this setting, instead of changing parameters on the network parameters outputted by F sub beta, G is going to operate on the hidden vector as well as beta G. Right?
Exactly, yeah.
So what exactly is beta G using that as network parameter?
Yeah, so there's a few different ways that you can think of this. Theta G might be something that's completely separate, that's optimized alongside the parameters of F. It could also be things that are something that's shared with F. So if you essentially just kind of collapse these two things together, then you can view it as just a single recurrent neural network that has that kind of shares all of its parameters, and HI just corresponds to the recurrent state of that RNN. Now, speaking of RNNs, one natural question is, like, this is a kind of one way to represent it. We have a black box neural network that takes as input a data set and a new test example and outputs predictions. Now, what architecture should we actually use for F theta? There are a variety of choices here. One example, or one of the kind of initial examples that looked at this kind of problem used either LSTMs or what's referred to as a neural Turing machine, which has this kind of form of external memory that it's using to kind of in the learning process. Now, a more recent architecture that I think is quite nice is something that instead of uses some sort of kind of recurrent neural network or an external memory mechanism, is what it does is it just takes all the inputs from your training examples and runs a feed-forward neural network on each of those training examples, and then averages the predictions, averages the embeddings of that feed-forward network into a single context. And then that single context is used by the network G in order to make predictions. So does anyone have any thoughts on why something like a feed-forward and then averaging architecture for computing the context might be better than something like a recurrent neural network? Yeah.
First, the recurrent model assumes that there is one ordering of training data, which is not necessarily the case. And so the average, on the other hand, is the permutation problem.
Yeah, exactly. So a recurrent architecture is going to assume that there's a particular ordering to each of the data sets. But in reality, a data set is usually a set, not a sequence. And a feed-forward and averaging architecture will essentially encode the fact that data points are permutation invariant, and it doesn't matter the order of the particular data points. And so this is kind of the main advantage of an architecture like this. One additional advantage is that it is often computationally cheaper to run feed-forward and averaging because you can completely parallelize things, whereas in recurrent neural networks, you can't parallelize each step as easily. But the permutation invariance is really the main benefit. Yeah?
Could one issue also be that if you have a large enough information, suppose because it's the RNN to forget some of the previous examples?
Yeah, definitely. So if you have a really large support set, an RNN can certainly forget things over time, whereas a sort of feed forward and average, it can sort of also forget things in some way, but it's not going to be forgetting in a sequence-dependent way. Okay, and then there's also some other architectures that people have used as well, other kinds of external memory mechanisms. People have also used things like attention as well, and temporal convolutions. Things like attention are also nice in the sense that they are also permutation invariant, depending on some of the implementation details. Okay, and then if you actually run the architecture on the far right on a few-shot image classification problem, like the omniglot dataset, which is a character recognition dataset, you can see that you can perform one-shot 5-way image classification with around 99% accuracy for new characters that it's never seen before. So it can essentially learn to recognize new characters with just a single example per character, which is pretty cool. And then beyond kind of the character recognition task, we can actually also look at the mini ImageNet task. This is actually the exact example that I was showing on the previous slides. And an architecture like the one on the far right gets around a 55% or 68% accuracy on a 5-way classification problem when you're either given 1 example per class or 5 examples per class. Cool. And so in homework 1, you're going to be implementing kind of the data processing training setup essentially for these kinds of few-shot image classification problems. You'll implement a very simple black box meta-learner, and then also just train a few-shot omniglot classifier and hopefully get numbers that aren't too far off from the numbers that we saw there. Great. Okay. Any more questions, or I'm thinking about running through an example. Okay, so I'll run through an example, and in particular, in your homework, you're going to be using the omniglot dataset. This is a dataset that has 1623 characters from 50 different alphabets. And so an example of some of the alphabets are shown here. And each character has 20 different instances. So essentially, they had 20 different people write that character, and for all of the characters in the data set. And one of the things that's kind of cool about this data set is it has many different character classes and only a few examples per character class. And in some ways, this is kind of like the transpose of a lot of common data sets. For example, it's kind of like the transpose of MNIST, because in MNIST, you have 10 classes and you have thousands of examples per class. And I also think that the statistics of a data set like this are actually much more reflective of the real world, where you have kind of very broad data and a very small amount of examples per class. For example, kind of probably over your lifetime, for many objects, you probably haven't seen like thousands of different instances of that object before. You've probably only seen, well, depending on how old you are, maybe you've seen only a few instances, maybe you've seen maybe 100 instances, but probably not a ton. Okay, so I want to run through an example from this problem, and this I think should be quite helpful for your homework. So let's say that we're doing kind of 3-way one-shot classification, and we want to be able to do this on omniglot. And so at test time, or at meta test time, we're given a new task, and we have a training data set for that task, which will be 3 different images, maybe A, B, and C from the English alphabet, and we'll assign a label for each of these images, maybe y equals 0, y equals 1, and y equals 2. And then we also have a test example, which will be an image for maybe A written in a slightly different way. And your goal is to be able to predict kind of the correct label for this, which is y equals 0. So this is what we have at meta test time. And then I'll do all of meta training on this whiteboard. So kind of during meta training, what should happen? So maybe the English alphabet is held out, or at least these characters from the English alphabet are completely held out. And so what is maybe kind of the first thing that we should do during meta training? if we're, or if we kind of want to compute a gradient step on our network, what's the first thing that we should do?
Sample an alphabet.
Yeah, so sample an alphabet. I'm going to do something a little bit more crude, and simply we're going to kind of put all the alphabets together. We're going to sample 3 different characters. They could be from the same alphabet. They could be from different alphabets. And we're going to be in the setting where we're just going to kind of train for the 3-way one-shot classification problem. So that's why we're going to be sampling 3 characters. And then we're going to be sampling multiple instances per character. And because we're in the one-shot setting, we want to sample at least 1 instance for the support set. And we also need to be able to sample some instances for the query set. And so we're going to sample kind of 2 images kind of per character. Can everyone see this, by the way? Is this big enough? Cool. Okay. And then we can just sample these at random. And then we need to, maybe I can draw this out. Maybe we have like alpha, I guess these actually are from the same alphabet, alpha, beta, gamma. And then we'll also have, we'll sample other instances that are maybe drawn slightly differently. Then once we have these samples, we need to use some for the support set and some for the query set. So we will kind of assign these to be all for the support set and all of these for the query set. And then we'll also need to assign labels for each of these. So maybe we'll give this a label of 2, a label of 1, and a label of 0. And likewise, this will have a label of 2, a label of 1, and a label of 0. Okay, and then from here, we're essentially ready to actually pass this data into the network. So this is the kind of the data processing step. And then once we have this, we'll essentially kind of pass dtrain into our neural network. We'll also sample one of the examples from dtest. So maybe it's, this will be this image right here. And note that when we pass in dtrain, we're going to be passing in both the images and the labels. Whereas here, we don't want to pass in the label because we don't want to give it the answer, right? So we'll pass this into the network as well. And then it's going to predict y hat. And then we're going to compute how good y hat is. So we'll have some loss function that compares y hat to the true label, which is 2. And then we can take the gradient of this with respect to theta. So maybe there are weights theta here. And we'll use this to update the network. Does that example make sense? Do people have any questions? Yeah.
Why are we allowing, when we sample 3 characters, why are we allowing that from different alphabets on using each task, like a separate alphabet?
Yeah, so the question is, why are we allowing it to potentially sample classes across alphabets? And shouldn't each task be a different alphabet? There are different ways to design the problem. And it is very valid to essentially kind of keep tasks constrained to individual alphabets. And when I wrote these, it was actually constrained to the alphabets. But one thing that can be helpful is if you don't constrain it to an alphabet, then you can essentially get more data, more tasks. And so it's essentially kind of a form of task augmentation in the sense, which is that instead of only considering tasks within an alphabet, you could also consider tasks that are classifying examples kind of across different alphabets as well. And this will essentially generate more tasks for meta training. And then in the homework, we will also be, we won't actually be holding out an entire alphabet. We'll just be holding out characters from across different alphabets. In a very realistic scenario, maybe it is actually an entirely new alphabet that you want to be able to test on. And in that case, you would actually, if you want to prepare for that scenario, you do actually want to hold out an entirely distinct alphabet during the meta training process to test whether the method is actually good at that.
was asking that is because if they're like allowing this kind of like augmentation, then I don't see the benefit of like the meta learning approach as opposed to just like putting everything in one data set and just training something on that.
Yeah, so with the form of task augmentation, you're still essentially like preparing the method to be able to quickly classify examples for a new alphabet. And so maybe during this meta training process, you don't actually have data for the test alphabet available, and you want it to be able to make predictions for a new alphabet kind of on the fly. If you do have all of the alphabets available ahead of time, then you can also use a multitask learning approach rather than a meta learning approach. Yeah?
So for example, in this case, we have multiple instances of each character. So is it like, is this standard to like, for example, if our target task is one-shot learning, one-shot classification, is it like our meta training tasks usually also going to be one-shot?
Yeah, so typically if you want to prepare it for one-shot learning, it's good to give it one-shot learning tasks at meta training time, because that will kind of prepare it for exactly what it will see at meta test time. You can also train it on variable shots, like some tasks that are one-shot, some tasks that are 5-shot, some tasks that are three-shot, and that should in principle also prepare it for different kinds of tasks, including one-shot tasks. One thing that you want to avoid is if you train it for 5-shot tasks and then test it on a one-shot task, it probably won't do well in that case because you're training it to be able to learn from large data sets and then asking it to be able to perform a task where you only have a small amount of data, and so you're not preparing it for what it will see at test time. Yeah?
In that case, isn't it always better to train it like, on one-shot tasks because it's like the hardest thing that you ask it to do?
Yeah, that's a great question. So actually, people often do exactly that, which is that you train it for one shot, and then you test it for maybe one shot or more than one shot. And one shot is the hardest setting. And it often actually prepares it for the one shot setting and also for settings that are a bit easier than that. Yeah?
Also, you would simply practice IIT if you're doing that. Saying that that's going to train on multiple key shots, values, and then only testing one shot based on IIT. So it's also a different problem.
Yeah, so if you train it on like 5-shot and then test it on 1-shot, you're breaking the IID assumption, and that's exactly why it performs poorly. It is valid to still train it on variable shot as long as the thing that you're going to be testing it on is a part of that and is sufficiently represented in the kinds of tasks you're training on.
I think I lost that. Can you just breaking the IID? Didn't follow.
Yeah, so the question is, how is what I said before breaking the IID assumption? So if all of your tasks are 5-shot learning tasks, and at test time you're given a 1-shot learning task, then the 1-shot learning task or problem isn't actually isn't represented in the distribution of tasks that you see during training. In that sense, one of the things that's kind of interesting about task distributions is it's not just like what's in the data and the loss function, it's also the size of the data set as well.
So why is that a problem in that direction, but not a problem in the, like, I don't mean, I guess, like
yeah.
Why is that a justification for why it's not to be fine from one instead of some other justification? Because if you're doing 1 to 5, you don't care about that at all.
Yeah, so in practice, training on 1-shot and testing on 5-shot actually still works pretty well. In theory, it shouldn't work well in some sense because you're training it for something and not testing it on something. The reason why in practice it works well is you're kind of testing it on a setting that's easier than the training setting. I guess that one thing that I should also mention is if you're using an RNN, using an RNN and you train it for 1-shot and then you test it on 5-shot, if you're rolling out the RNN for longer than you trained it for, it will actually perform very poorly. And so for RNN type methods, you don't want to go from 1-shot to 5-shot. But for a lot of other meta learning methods, they usually work well when you train on 1-shot and test on 5-shot because of how they add structure into the algorithm. Yeah.
I'm a little bit confused about the application of something like this because it seems like it would be I guess what we were saying it was like 1-shot, where it's like given this character, what task label is it, as opposed to giving these 5 characters what label is it? Does that make sense?
I'm not sure I understand. Can you repeat that?
So basically my question is, I'm a little bit confused on why this type of stuff would be used in any application, because from what I'm thinking of is, if I take a picture of a character, I want to know what that character is from handwritten to an actual using code sort of thing. And then so I'm a little bit confused how doing something like putting that character from taking 1 or 2 would look at that.
Got it. So the question is kind of talking a little bit more about kind of a real world use case of this and so forth. I guess the typical use case of this is one where maybe you have you take a picture of images. It is it's not a 0-shot setting. Like if you see a character that wasn't seen in the training data set and you take a picture of it, it's not going to be able to classify it because it's just simply not enough information. And so the application is something where maybe you have maybe you want to deploy something in a new country and you collect a small amount of data for characters from that country, maybe to help with the postal service or something like that. And you don't want to collect a massive data set for that. You want to just collect a very small data set because that will be very cheap. And so you take images of characters from that new alphabet and then use that to train a classifier so that you can deploy that classifier on all of the mail from that country or something. Does that make sense?
Well, I think so.
Okay, great. Yeah.
Mostly using a neural network to output another Delphi files. Are we contributing to Delphi files?
Yeah, so the question is, what are the implications of using a neural network to output the weights of another neural network? Are we kind of contradicting the inductive bias of neural networks? I think that it's possible, I guess, in general, this sort of idea of outputting weights of another neural network is referred to as hypernetworks sometimes, and it's possible that this will not retain some of the nice inductive biases of neural networks when the weights come from another neural network. And we will actually see in the kind of coming lectures approaches that have better inductive biases, including metric learning approaches and more optimization-based approaches where the weights aren't coming from another network. Yeah, so the question is, how many tasks do we need? In general, like I said before, the more the better. And it ends up being somewhat problem specific and domain specific. If the tasks are relatively simple, you might not need that many. But if you have a very broad distribution of tasks, then you're going to need more tasks to cover that broad distribution. There is some work that tries to theoretically characterize how the number of tasks impacts performance. I think that there's some work by Rich Zemmel, for example, at Toronto that studies that. And they do look at some bounds, but that's kind of beyond what we'll look at in this course. Okay, and then a couple more things worth mentioning here. This was an example in Omniglot. There are also a number of other image recognition data sets like CFAR, CUB, SLEBE, and Orbit. Orbit's actually a pretty nice example. It's coming from the standpoint of trying to build classifiers for blind or visually impaired users, where the user will take pictures of their items, take only a few pictures naturally, and then you want to be able to allow them to build a classifier for their items using those pictures. There's also benchmarks that are outside of the image recognition domain. Here are a few examples, and if you're interested in looking at data sets for your projects, these benchmarks could be interesting. Okay, and then to summarize kind of the black box approach and the pros and cons, these sorts of networks are very expressive because they're essentially parameterizing a learning procedure using a potentially very large neural network. It's also very easy to combine this kind of approach with a variety of different problems, including supervised learning and reinforcement learning. There are some downsides. So in general, you're trying to learn how to learn from scratch, essentially. You're trying to learn this learning procedure from completely randomly initialized weights of a neural network. And this leads to a fairly challenging optimization procedure. And as a result, it can sometimes be data inefficient in terms of the tasks that you need for meta training. And so there are other ways that we can essentially represent these learning procedures. And next time on Wednesday, we're going to be looking at how we can essentially treat it as an optimization procedure and parameterize an optimization procedure as part of the learning process rather than using a neural network to represent the entire learning procedure.